This presentation is on the nature of atoms, and then we'll continue on to begin the discussion on the periodic table. Before we get into the atom, we have to discuss waves. The first thing we want to discuss about waves is the wavelength, which is designated by the Greek symbol lambda and is an actual length, so you measure it in meters or nanometers or some relation. The wavelength is the distance between the two equivalent points on the wave, whether that be the peaks or the troughs or midpoint, doesn't really matter. The wavelength is the same, but it's the distance between two repeating points. The other thing is the frequency. The frequency is how many of those wavelengths are passing a given point in a period of time. So if these waves were moving to the right, you would count how many peaks or how many troughs went by in a second, and that would be your frequency, which has the units hertz or cycles per second, but we don't write cycles, so the unit ends up being seconds to the -1 or just 1 over the second. And for waves traveling at the same velocity, the longer the wavelength, the smaller the frequency, so they have an inverse relationship. To prove that light traveled like a wave, there was the double slit experiment where you have your wave fronts going in. So over where the red arrow is, these are representing your wave fronts, which is the peaks or valleys or the repeating part of the wave. So they're all moving parallel to each other, but when they go through the openings, they spread out. You can picture like water going through an opening and spreading out on the other side. So the waves will do the same thing. And then you get this interference pattern where the waves will overlap each other, and sometimes they add to each other if they're both high points of the wave, and sometimes they'll subtract from each other if one's a high point, one's a low point. So what you end up on a screen is you get these bright and dark spots that are repeating. So that's what we call the diffraction pattern. So any wave will create this diffraction pattern. You could even do it in water. So when they did this experiment with light, they discovered then that light was in fact traveling like a wave. So when we look at electromagnetic radiation, we know that it can travel through a vacuum. It travels at the speed of light. We named it that because light was the first one we discovered. The speed of light was calculated through multiple experiments to be a little less than 3 × 10 to the 8th meters per second, but it rounds to that. It's 2.998 × 10 to the 8th meters per second. It travels as a wave, which we already discussed, and a particle called a photon, and we'll discuss how they prove that it travels like a particle as well shortly. It has a frequency that's related to the wavelength by the equation C equals lambda V. C is the speed of light. It's a constant. Lambda is the wavelength, and V is the frequency. So we mentioned that it's an inverse relationship, and this equation shows that. It has an energy related to the frequency by the equation E equals hV, where E is the energy in joules, and H is Planck's constant, which is 6.626 × 10 to the -34 joule seconds. It's actually a unit for angular momentum, meaning the momentum of a object going in a circle, which is appropriate for how they first viewed the electron. And you can see that energy and frequency then are going to be directly related. So if the frequency is higher, that means the energy is higher. This is the electromagnetic spectrum. It has the wavelengths across the top and the frequencies across the bottom. So you can see as the wavelength increases, the frequency goes down. These are all the different types of electromagnetic radiation that we identify, although the boundaries between them are a little blurred. But your lowest energy waves are radio, and then increasing in energy is microwave. More than that is infrared. Then there's that little band of visible light, which is what we can see. Above that is ultraviolet, then X-rays, and then the highest energy radiation is gamma rays. And somewhere through the ultraviolet and beyond is where you get to the ionizing radiation, which means that when it hits atoms, it can eject electrons, and that's the radiation that's dangerous to us. Visible light, you can see the lowest energy visible light is red, and the highest energy is violet. And we measure the wavelengths of visible light in nanometers, 10 to the -9th meters. And that's just where it falls. So the beyond that then, on the low end is where the infrared begins, and beyond that on the high end is where the ultraviolet begins. This is an explanation of the photoelectric effect. Light, monochromatic light of one color would be shined on a metal surface, and sometimes the electrons would get enough energy to jump off of the metal surface and head towards the positive terminal, and then that would complete the circuit and you would be able to measure a current. what it turned out was that only certain wavelengths of light have the energy necessary to make the electrons jump. And it was determined that intensity had nothing to do with it. So really, really bright red light wouldn't make the electrons jump, but really, really faint violet light would make the electrons jump off of the metal. And so what it was determined from this by Einstein was that photons are traveling with the light. So light's acting like a particle, and you can picture these as little packets of energy. And if an individual photon doesn't have enough energy, then it won't give the electrons the energy necessary to jump. And so they'll stay there. But if that one photon has enough energy, then it will cause the electron to jump away, pull away from the metal atoms, and complete the circuit. It's almost like water balloons. You know, if it's not filled enough, it's never going to break. If it's filled a lot, then when it hits something, it's going to break and release all the water. So that's the way the photons were kind of pictured, as containing that energy. And from this experiment, it was also determined that only certain energies are possible, whole number multiples of hv. So Planck was the one who discovered that, and that's where h became Planck's constant. But what it basically said is that there's only certain energies that are available, 1 times that, 2 times that, 3 times that, and nothing in between. So it was beginning this idea of quantizing energy where only certain ones are possible. So Bohr took that idea, and they knew about bright line spectra, but Bohr was the one who explained how the bright line spectra works. So you have these individual lines that appear when you run electrical current through a gas, one type of gas. So in this case, there's the bright line spectra shown for hydrogen and neon. And then you run the light through a prism, which breaks it up into the different wavelengths. And instead of getting a complete spectrum of all the colors, each element gives its own unique spectrum or fingerprint. And so Bohr looked at this and said, well, based on the quantized energy levels, that must mean that the electrons can only have certain energies in their orbits. And so he looked at it this way, that when you put the energy in, it causes the electron to jump from a lower energy level to a higher energy level. And it will only jump if it has the exact energy. So this chart over here is showing the possible energy levels and how much energy in joules there is per atom. Notice it's negative because we're measuring the electron being completely free as having no energy. But as it gets closer to the nucleus, it actually is at a lower energy state. It gives energy back as it gets closer. So you're measuring how much energy you have to put into it to pull it away from the nucleus, and that's why it's a negative. So you put the energy in, it jumps up to a higher energy level, and then it can't stay there forever, so eventually it releases that energy back and drops back to the lower energy level. And when it releases that, it releases it as monochromatic electromagnetic radiation. So it could be color of light, or it could be infrared or X-rays. It all depends on which energy level and how much energy is involved in a transition. So the bright line spectra are just the transitions that we could see in the visible spectrum. In this case, energy level 3 to energy level 2, and that would be, if we go back to the previous one, that would be one of your higher transitions, so that's going to be one of your violet ones. And then there's a point where if you give too much energy, the electron just leaves the atom. That's this N is infinity. That means you've ionized the atom. So anything above this is ionization, and that's what happens when you get into the far ultraviolet and X-ray. The electron just leaves. It can't stay and come back. And we call this an excited state when you jump it up, because it's not where the electron wants to be. You had to put energy into it to get it to go there. All right, so after the Bohr model, we have these electrons in very specific orbits going around the nucleus, and each orbit has a specific energy level. So further experimentation was done because Bohr just didn't explain everything well enough. So de Broglie looked at the experiments with the double slit and the photoelectric effect and said if light, which we thought was just a wave, has particle properties, then maybe what we thought were just particles have wave properties as well. And so he did some experiments with electrons. Eventually other people did the double slit experiment using electrons instead of light. And sure enough, they got the interference patterns, which proved that electrons have wave-like properties. So de Broglie concluded from that that all matter, all particles, have wave-like properties. and it's based on the equation lambda equals Planck's constant over mv, mass times velocity, which is the momentum of the particle. But large mass particles, if you plug your mass in there, you'll see that the wavelength is so small that you won't observe anything. But for electrons, where the mass is very, very small, even though the velocity is high, you still are going to get measurable wavelengths from that. So the electron acts like a wave. So because the electron acts like a wave, we never actually know where it is in its particle sense. So it's impossible for us to know both the position and the momentum of the electron at the same time. If you measure one, you're not going to know the other. And that's what Heisenberg's uncertainty principle is. It means that the location of the electron can only be determined based on probabilities and not certainties. And that's the foundation for everything we know about the atom today. So a scientist by the name of Schrödinger provided us with a wave function, which is just a mathematical equation that gave us information about the volume of space that the electron is most likely to be found in. So it's a combination of wave mechanics from physics and probability and statistics from math, and putting the two together, he was able to generate shapes of possible orbitals. And that's what they referred to them as orbitals. Even though the electron's not orbiting, they still used that kind of idea and called it the orbitals. And these shapes are going to be different sizes for different amounts of energies. They're also going to have different shapes based on different amount of energies. And so it makes the electrons have a much more complicated life in the atom. But it gives us the quantum mechanical model, and with some certainty, it gives us the shape of the hydrogen atom and the electrons that are in there. The issue with Schrödinger is that it's an approximation because it's based on probabilities. And when you start adding multiple electrons, the equation becomes very, very complicated. So even though we understand that Schrödinger's equation works, we can't accurately predict anything about most complicated atoms, and especially once we start getting into bonds and things like that, it's very difficult to picture and know exactly what the electrons are doing and how they're doing it. But it gives us a close enough approximation that we know with some certainty, maybe 90% or 95% accuracy, what the electrons are doing at any moment in time. So I'm going to stop with the quantum mechanical model there. We'll talk about the complexities of it in class and some of the other things that we have to do with it. But it led to our understanding of the periodic table. The first accepted periodic table was created by Mendeleev, and this was done in the 1860s. So this was before we knew much about the atom. We were still dealing with Dalton's atom at this point, which is just a sphere with no charges. So what they did is they just did lots of experiments looking at the properties of the elements and how they interact, and grouped them by their similar properties, and then arranged them also by their masses. Mendeleev was not the first and only person to do this, but the reason why he got credit was when he arranged his table, he was able to predict the existence of elements that hadn't been discovered before, and using the properties that he had figured out from the other elements in his table, he predicted what some of the properties of the unknown elements might be. And since he did that with some accuracy, that's why he was given credit for his table, even though other people were kind of doing the same thing. They just didn't show how useful it was. Our modern table is aligned with quantum mechanics and electron configuration, so when we do that, we'll be able to explain more about the periodic table. But as it turns out, because electron configurations and electrons have everything to do with the properties of the elements, it still is arranged similar to Mendeleev, because they are still same group or same column will have the same properties. And instead of using masses, which is all Mendeleev had to use, eventually we discovered protons and now have the table organized by increasing atomic number. All the trends of the properties of the elements are completely related to the electron's attraction to the nucleus then. So the reason why elements have different properties is because of how strongly the elements attract their electrons and hold on to them. So the way we measure that is called the effective nuclear charge. So all electrons are attracted to the nucleus individually. All right, so the amount of electrons doesn't have too much of an effect on how much the electrons are attracted if you look at it as individual attractions. Obviously, electrons repel each other, but they don't see the whole strength of attraction of the nucleus because there are other electrons in between them and the nucleus. So what happens is we say the inner electrons shield the positive charge of the nucleus from the outer electrons. And so you basically take the number of protons, or the amount of positive charge in the nucleus, and subtract from it the number of inner electrons, not the valence electrons, just the inner electrons in the lower energy levels than the outermost, from it. And then what's left over is the effective charge that that outermost electron sees. So there's the equation, Z effective, which Z just means positive charge, equals Z, the number of positive charge from the protons in the nucleus, minus S, which is the number of inner electrons. So for sodium, sodium has 10 inner electrons and 1 valence electron. And so since sodium has 11 positive charges and 10 negative charges inside, you say 11 minus 10 is 1. So this electron out here sees a positive charge of just 1. So that's its effective nuclear charge. It's not perfect. Doesn't actually calculate perfectly that way because some of these electrons on the other side are going to lower it and some of these electrons on this side are going to raise it. And so it's not really perfect, but it's a good estimate and it's enough for us to continue our discussion. So if you look at the charge of the nucleus, that's what the red is essentially, what the 1s, or the closest electrons to the nucleus, feel as their charge. But if you start looking at the outer electrons, you see that you have this drop in the charge once you get past element 10, which is neon, get to sodium and beyond. You see that the effective nuclear charge goes back down essentially to 1 and then increases. And these 3 different colors are just 3 different ways for calculating that because it's not perfectly 1, 2, 3, etc. But it's pretty darn close. The green is the 1, 2, 3. The others are what you actually calculate. So the size of the atom is called the atomic radius. As you go down a group, the atom gets larger since the effective nuclear charge is the same in the whole column, but the outermost electrons, because there are more energy levels, are farther away from the nucleus than there would be in the previous row. So because the electron's farther away but feeling the same charge, that distance causes the overall pull on that electron to go down. So the electrons are less attracted to the nucleus, which means the atom will be larger. As you go across a row, the effective nuclear charge increases because they're pulling on the same valence electrons, but you have more protons in the nucleus. So that pulls all the electrons in the atom in tighter to the nucleus, and that causes the radius to get smaller. This is probably the most important trend. Once you know this trend, then the rest of them all kind of make sense. Ionic radius, we know that cations have lost electrons, and when they do that, most of the time they are losing their whole outer energy level, at least for the majority of the ones that we deal with. And so by losing that whole outer energy level, they have a greater effective nuclear charge on a smaller number of electrons, which makes them significantly smaller. In fact, a sodium ion will be smaller than a neon atom because it's got more protons pulling on the 10 electrons at that point. Anions gain electrons. The added repulsion of the extra electrons makes them larger because they have more repulsion between the like negative charges, but their effective nuclear charge hasn't increased any, so it causes the whole electron cloud to expand, so they get bigger. And when you look at isoelectronic species, or species that all have the same number of electrons, you can figure out their radii compared based on a number of protons pulling on the electrons. If they're isoelectronic, they all have the same number of electrons. So the one with more protons is going to be smaller because it's going to be pulling on the electrons harder. Ionization energy is the amount of energy needed to remove one electron from the ground state atom in its vapor phase. So we vaporize the element and turn it into a gas, and then we put in energy to pull an electron off. So it's related to the effective nuclear charge and the radius. The higher the effective nuclear charge and the smaller the radius, the harder it's going to be to remove electrons. It's just simple, right? It's got a stronger pull, so you're going to have to put more energy in to pull it away. So when we get to successive ionization energies, that means we look at, well, how much energy did it take to remove the first one? and then the second one, and then the third one. And each one's going to take more energy than the one before it, because each one then will be closer to the nucleus. Because when you pull an electron out, the repulsion goes down, all the other electrons get closer to the nucleus, and now it's going to be harder to pull the next one out, and the next one out, and the next one out. Plus, you can change energy levels or sublevels. So when you go and you pull out that last electron from the valence shell, that won't be very difficult compared to pulling out the first electron from the first inner electron shell. And so that's going to be a tremendous amount of energy to pull out. So you see a big difference in the amount of energies it takes to remove electrons, and by those differences you could actually identify the elements that you're dealing with. Electron affinities is the energy change when an electron is added to a gaseous atom. For nonmetals, this would be very negative. For metals, this would be slightly negative. When you're adding electrons to filled and half-filled energy levels, this can at some point even be positive. The bigger the atom, the less negative the affinity. So basically, some atoms, when you add electrons to them, will give you tons of energy, like a fluoride or chloride forming a fluoride or chloride ion. But others, when you add an electron to it, they didn't really want it. So that doesn't give them, they don't give you a lot of energy when you do that. And in some cases, they'll actually need energy to be absorbed in order to do that. Electronegativity is based on an equation that was developed to rank elements by their attraction for electrons, mostly in a bond. It's on a scale from 0 to 4, 4 being the highest attraction for the electrons. It is related, and part of the equation is related to the ionization energy and the electron affinity, but there are other factors that go into that, so it's a fairly complicated equation. But basically, though, the smaller the atom with the higher effective nuclear charge will have the higher electronegativity. And so by using that as a prediction, we can then understand a lot of things about bonding and polarity and those things that we've already talked about, but now we'll talk about it on the specific atomic sense or molecular sense as to where it comes from. So the summary of the periodic table is basically, if you're talking about a classification of an element and you say that there are metals, metals tend to be larger atoms that have the smaller effective nuclear charge, so they will lose electrons when given the chance. Since metals don't hold on to their own valence electrons well, they create that sea of electrons that we already talked about. This is why metals are good conductors of heat and electricity. They're malleable and they're shiny. They have a luster to them. The opposite is true for nonmetals. They have a high effective nuclear charge, so they hold on to their electrons strongly, so therefore they don't conduct heat and electricity because there's no moving particles to do that effectively. They tend to be brittle, and they tend to have dull colors because they're absorbing the light instead of reflecting it the way the sea of electrons just reflects it. That's what makes the metal shiny. And then you have metalloids or semimetals. There are 6 of them that everybody agrees upon, which is boron, silicon, arsenic, tellurium, germanium, and antimony. And they can have properties of both, and those properties can be varied based on the conditions you put them under. The last summary is the farther down a column you go, the more metallic the element is, because it's getting bigger as you go down a column, so it's harder and harder for it to hold on to those outer electrons. And that's why when you look at like column 14, you start with carbon at the top, which is a non-metal, and then you hit silicon and germanium, which are metalloids, and then you hit tin and lead at the bottom, and those are metals. So they become more metallic as you go down. So there's a chance that the element under astatine will act more like a metal than a halogen if we actually were able to figure out the properties. In addition to that, as you go across a row, they become more non-metallic. And so if you understand all those trends and you understand that, then you understand a lot of the bulk of chemistry and classification. So that concludes this presentation. More to come.